I'm Toshikazu Ishida. My presentation title is Commutativity of Composition of Some Elementary Cellular Automata on Monoids. Introduction. Recently, cellular automata often mean cellular automata on groups, and mathematical theory of cellular automata has been developed related to theory of groups. Hedlund, Moore, and Driscoll show some algebraic properties of cellular automata on semigroups. The analogy between cellular automata and propositional logic has been recognized by Inuchi et al. We have introduced cellular automata on monoids, making use of formula in propositional logic instead of local function in previous research. The local function of a composite cellular automata can be expressed as multiplication of propositional logic. However, many properties of composite cellular automata on monoids have not been clarified. This slide shows relation between cellular automata and propositional logic. Set of state of cellular automata is correspond with set of true values. Cell space of cellular automata is correspond with set of propositional variables. Configuration is correspond with variation. Local rules of cellular automata is correspond with formula of propositional logic. Our work are following. We examine logical formula on commutative monoids as local functions of elementary cellular automata. We discuss the commutativity of the multiplication of formula and describe the conditions for formula that can satisfy the commutativity of the composition of some elementary cellular automata on commutative monoids, which is commutable for the composition with cellular automata of local function having one cell in its neighborhood. And we provide example of composition that can satisfy commutativity for elementary cellular automata on commutative monoid. We also show what conditions can satisfy the commutativity of the composition of inverse function of reversible cellular automata on monoids. First, I show the definition and proposition of propositional logic. Let X be a set of propositional variables and let bottom and implication be logical symbols. Formula on X are defined by BNF. Formula A consists of variable X or bottom or implication of formula A and formula A. Those symbols, negation, burn, disjunction, conjunction, equivalence, and exclusive OR are introduced by the usual abbreviations. In what follows, we assume that Q is a Boolean algebra of true values, for AB is element of Q, and operators implication, equivalence, and exclusive OR on Q is defined by those formulas. I show the definition of variation. A variation M for a set X is a function X to Q. The true value MA of a formula A on X by M is inductively defined as follows. For all element X of X, Mx is value of X, and M prime is 0. For formula A and B, M A to B is equivalent to implication MA and MB. If MA equals MB for all variation M, we write as this. Next, I define cellular automata on monoids. In what follows, we assume that M is a monoid with a unit element E, and the set of all formula on M is denoted by Fm. I define shifted formula. For a formula A and element x of M, the shifted formula xa is defined by induction on A. For element y of M, xy is monoid multiplication in M. X bottom is bottom. For formula A and B, x A to B is shifted formula xa to shifted formula xb. I show definition of configurations. A function M to Q is called a configuration on M in context of cellular automata. We denote by m's power of Q is the set of all configurations. For value Q, the constant configuration Q hat is defined by Q hat x equal Q for all element x of M. Q hat shows that all states of M are equivalent. In this slide, we define transition function. For formula A on M, define a function Ta by follows. For configuration M and element x of M, the function Ta is called the transition function defined by A on M, and A is called the local formula. Since a local function of cellular automata with binary state is a Boolean function with finite variables, it has a disjunctive normal form. Thus, the class of cellular automata defined by logical formula contains the class of binary cellular automata defined by local function. I show example of cellular automata defined by formula. We assume capital N is the additive monoid of all natural numbers. Let M be the set of all n's power of x, and N is set consisting of 0's power of x and square of x. Then M is commutative monoid, and let the local function f be defined according to the following table. The disjunctive normal form f of function f is this formula, and the simple formula for A is this formula. This number is Wolfram number. For each cell's state compute by following. So for element x, transition state is computed by shifted formula. Next, I define multiplication formula and show proposition. Let A and C be formula on M, and x is an element of M. The multiplication A and C is inductively defined as follows. Multiplication of x and c is shifted formula xc. Multiplication of bottom and c is bottom. Multiplication of A to B and C is multiplication of A and C to multiplication of B and C. For multiplication of formula, following properties hold. Disjunction, conjunction, and exclusive OR satisfy distributive law. For multiplication of formula, it satisfies associative law. For all formula A, C, composition of transition function defined A and C is the transition function of multiplication of A and C. In this slide, I show the example of multiplication of formula. Formula A corresponds with this local function is disjunction of 0's power of x and x. formula B correspond with this local function is negation of 2th power of x, then multiplication of a and b, and multiplication of b and a are following. These three show a and b. These three show multiplication of a and b, and multiplication of b and a. For space of variables, shifted formula substituted. A transition function Ta defined by a formula A is reversible if it is bijective with inverse Ta equal Tb for some formula B. A formula A is reversible if there exists some formula B on M so that multiplication of B and A equal unit element and multiplication of A and B equal unit element. Formula A is reversible if and only if transition function defined by A is reversible. For reversibility, following proposition holds. Let A, B, and C be formula on monoids. Then, if multiplication of A and B equal unit element and multiplication of C and A equal unit element, then B equals C. A and B are reversible. Then multiplication of A and B and multiplication of B and A are reversible. In this slide, we show properties of commutativity of multiplication of formula. Let M be a commutative monoid. X is element of M and A is formula on M. Then multiplication of X and A is commutative. Let M be a commutative monoid and X is element of N. So number of variation of A, B, C are 1. Then following hold. Next, I show properties of commutativity of composition of cellular automata. We assume M is set of nth power of x and a neighborhood N is set consisting of 0th power of x, x and square of x. Then the following holds. The composition of any cellular automata with local formula x is commutative. In elementary CA on M, the composition of any cellular automata and a cellular automata with the local function of number 117, 204, or 240 is commutative. Let BCD is formula that number of variation is 1 and x is element of M. Each composition of cellular automata with the local formula negation of x and cellular automata with these local formula is commutative. In elementary cellular automata, negation of x is correspond with the local function of number 15, 51, and 85. This formula is correspond with the local function of number 77, 113, 142, 215, 232. This formula is correspond with the local function of number 23 or 43, These formula is correspond with the local function of number 105, 150. We assume M is monoid, not confined to a commutative monoid. Let CAA and CAB with local formula A and B on monoid M be reversible. If the multiplication of A and B is commutative, then the multiplication of inverse B and inverse A is commutative. In this paper, we examined logical formula on a commutative monoid as local functions of elementary cellular automata. We discussed the commutativity of the multiplication of formula and described the conditions for formula that can satisfy commutativity of the composition of cellular automata of local function having one cell in its neighborhood on commutative monoid. We also provide examples of compositions that can satisfy commutativity for elementary cellular automata on commutative monoid. Finally, we explained the condition that can satisfy the commutativity of the composition of the inverse local formula of cellular automata on monoids, not confined to commutative monoids. Future work is following. We have focused on elementary cellular automata in this paper. We guess that those some properties hold for cellular automata on other monoids. We need to check it, and we need to formulate more computational laws of formula on monoids, and we should clarify conditions for cellular automata that cannot be created by compositions of cellular automata. Finally, we need to study which are the reversible cellular automata on monoids. It may also be necessary to determine whether well-known theorem and properties of cellular automata on groups hold in the case of monoids. Thank you for listening.